Hi guys, my name is Harsh Agrawal. This video is part of my digital assignment from the subject data structure and algorithm with our faculty, Dr. Kausar Ahmed. In this, I will be talking about binary search tree and also about what the project and additional learning I have been doing in this course. I will talk firstly of the basics of binary search tree and then go into the time complexity and how it is more efficient than other search algorithms. So let's get into the video.
Now, before we go into deeper knowledge of what is a binary search tree, let's first understand what is a tree. So, tree is basically a representation. So, you have a data like A, B, C, D in a stack, and you want to represent it in the form of tree. So, you can represent it like A, B, C, and D. So, this is a tree representation of any data. Now, what is a binary tree? Binary tree has a simple rule that at each level you can have a maximum of two nodes. So if I represent this as a form of binary tree, I get one at here, two at here, and one at the end because I cannot have two children for one specific root value. Okay. Now, how can we implement binary search tree? So implementation we have two ways. One is array or linear representation, and one is linked list. And for traversal, we can do it in the form of three ways. One is in order, pre-order, and post-order. Okay, so let's see how can we implement a binary search tree in an array or a linked list. Now, if we go to the implementation, first in linear implementation, we should note that the gap, like if root should have two children, but I only put one children there, then there is a gap in that binary tree. So that gap will be treated as a null space in an array. So I'll take a simple example and write it in both array and linked list ways. Okay. So let's take an example. I will draw a tree A. So now you can see that there is a gap after the C because I have not put one more children, and also in F and E also. So now what will happen if you write it as an array? So writing it as an array, we get A, B, C, D, E, F. Now after F there is a gap, so we put a small space and go for G. After G we can see that there is again a gap, so we put a gap and go for I. And after I we see that there is again a gap, and then we have J because there is a gap for F, left node of F, left tree of F. So we do put a gap and go to J. So this is an array representation. It's simple. Now moving on to the linked list representation, it goes something like this. The linked list, we draw it. You know the basics of linked list. So I'll just go and draw the structure. We have A, which is connected to B and C. So we'll draw two extra nodes so that we can connect it to both B and C. So one of this will be connecting to B, and one of this will be connecting to C. Okay. Now from B we have D and E, so we again need two nodes. That's why we'll make a blank node and finish it with E. So E we have connected. Now for D we again have two nodes, so we are going to connect D first. We don't have to cross it here because we have connection from E as well. So while connecting it, after that we will end. Now from this we connect to D. Okay, and D we have G and H. Now we connect it to G and H in a simple manner. We don't have to see the order is not important here, and then we have a cross. Now E will connect to I. You can see on the diagram that E is connected to I and there is a cross. Now for C, now C is firstly connected to F, so we connect it to F. Okay, now F is connected to J, so we connect it to J, and then it ends. So this is a simple linked list representation, and this is a array representation. Okay, so there are two ways now we can implement it. So we have done it. Now let's move on to the traversal part. So then I told you earlier that in traversal we have three ways. One is in order, pre-order, and post-order. So let's take a simple binary tree and see what happens. Now, first I'll tell you the order. In order, we have to take the left child first, then the root, and then right child. In pre-order, we have to take the root, then left child, and the right child. And in post-order, we have to take the right child first, then sorry, left child first, and then we have to take the right child, and then at the end root. Okay, this is the basic rule of writing in order, pre-order, and post-order. If I take a simple example, like just a simple one, ABC, this is a simple example. Now if I write it in order, I'll get I'll get sorry, BCA, BAC, because we have to take the left child first. So left child is B, then is the root, then is C. So BAC we get. Okay. Now in pre-order, we have the simple R, left, right, left child, and right side. So R is A, and then we have B and C. So we get a simple A, B, C. Now for post-order, we get the expression as BCA. So we have left child, right child, and the root. Okay, so this is a simple one. You have understand the basics of these three orders. Now we can also call it as infix expression, prefix expression, and postfix expression. So if I get a infix expression, and I am set to convert it using binary search tree, so I'll convert this the expression in binary tree using this rule, and then I will after converting it into binary tree, I will convert it back into prefix expression, but with this rule. So I get a prefix expression, but using binary tree, not using stack. Okay. So now I'll take a simple example and write the expression for all the three traversals. Okay. Now when I take an example, a good one. So A, B, C, okay, so this is a simple example. Now what happens if we write it in pre-order? Let's say first pre-order. Okay, so in pre-order, we write it as A, B, sorry, A, B, A, B, D, G, H, E, I, C, F, J. How? In pre-order, we know that the sequence is root, left child, and right child. So we take the root A, then left child B, then again the left child D, then again the left child G. Now then is the we have to take the right child root and the left child. Okay. So after G we go to H, then we go to E, and then we go to since A is already taken, we go to the right child. So right child when we go, we get C first, then we get F, and we get J. This is simple rule. Okay. Now move on to in order. In order, we will get G first, and then we'll get D, H, B, E, I, A, F, J, C. Same rule applies here. We know the order: left child, right root, and the right child. So we take the left child first, G, which is the leftmost child, and we go up, 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 and slowly we complete all the subtrees, and we go towards the right child from root. Okay. Now we go to post order. Post order, we again know the sequence. We will get G, H, D, I, E, B, J, F, C, A. Okay, so we know the sequence. We just go from there to there. Similarly in post order as well. Okay, now we know the basics about a binary search tree. Now let's see why binary search tree is better in many ways from any linear search or any different kind of searches. Why is it the best? is it efficient or not? Is it efficient than other search algorithms? Now, first the question comes that which search algorithm will you, which data structure will you take if you want to represent a set of data, then you want to search for data from it, and you want to modify the data. So the answer basically comes arrays, linked list. We can all search and modify data from arrays and linked list. Okay, but in this case, we have to consider the running time of these data structures. For array, the running time would be very high. I'll show you how. Look, like I take an array. Okay, so simple array. I'll take an example: 2, 4, 1, and 6. So this is a blank space. We just leave it, and the index values are 0, 1, 2, 3, 4. Okay. Now here it ends. Now, to search, we have to see from the first, and sometimes in the worst case, we have to search the whole array to get the final value. Like here, if I have to search 6, I have to start from 2, 4, and 1, and 6. So, if we take the time complexity for search of x, we will get big O of n, because we have to search sometimes all the elements also in worst case. Now for same for it goes for insert. Now we when go for insert, we have to insert it as a specific value. So we get suppose I want to insert 5, so I just insert it at the last. I don't have to check whether I have to put in a specific position. So we can simply guess that the time complexity will be big O of 1, because I don't have to search for everything and all the elements. I just have to put it at the last. Now, but for removal, what happens is that if you want to remove a specific value, what happens is, suppose I want to remove 4. For that, I have to replace 4 by 1, then 6 by 1, then similarly I have to keep replacing these elements, okay, the adjacent elements. So I can get 4 at the end and then I delete it. Okay, so for that we can see that it will go get a big O of n. Suppose I want to delete 2, so I have to change the whole array, and that's why I have to go through the whole array of n elements, and the time complexity comes to big O of n. Now time will not depend on the elements in insertion, so time complexity is big O of 1. In removal, we have to shift all the elements, therefore the in worst case it's big O of n. So the question comes, can we do something better than big O of n while searching, while removing? Can we do something better than big O of n? Now in an array we can perform search, binary search, if all the elements are sorted. Okay, so why do we need to binary search? Because for binary search, the time complexity is big O of log n, which is the best time complexity we can have. Okay, now let's see in a sorted array. Then we will go to the binary tree. For sorted array, we again take an example: 2, 4, 6, 9, 11, 15. Okay, this is a sorted array. Now in sorted list, if we have to insert something, we have to sort the array again after insertion. Okay, so let's try the index values first. Okay, so these are the index values. Now for search, it's big O of log n, because we are doing a binary search, and I'll show you how binary search works. But in a sorted array, we can definitely do binary search, and it comes to big O of log n. But while going for insertion or removal, we can see that after inserting or removing, we have to change the whole array. We have to sort the array again. So it again comes to big O of n and big O of n. So this is not better than the last one. It's simply searching is better, but insertion gets worse. First it was big O of 1, and now it goes to big O of n. So now, can we do something more better? For this, it comes down to the binary search tree. Now binary search tree, let's see the basics of binary search tree. We get that search, insert, and removal all have big O of log n as complexities. The cost is always big O of log n. Okay. Now this is in average case. We always take this as an average case, not in the worst case. In PST, we can show that average case can always be used and we can avoid the worst case by making sure that it is balanced. The binary tree is always balanced. Now let's see how BST minimizes cost for all these operations when balanced. Okay, so first let's understand what is a binary search tree. We talked about binary tree. So what happens in binary search tree is that it is a tree in which for each node, value of all the nodes in the left should be lesser, and value of all the nodes in the right subtree should be greater than the root value. Okay, so this is the basic of a binary search tree. Let's take an example with integers so you can get it easily. Okay, so integers, we take first we take a simple example. You can take any example, but I will take this example. It has a different range of values. Now we can show that each node of the left subtree is lesser and right subtree is greater than the root value. So root value is 15. Okay, so we can see that left, when we go to left, all the elements would be less than 15. So 10, 8 and 12 is less than 15. Now when we go to the left subtree, we should see that the root value is 10, and 8 and 12, the left 8 is less and the right 12 is more. So this part, left part, is perfectly alright. When we go to the right part, 20 is greater than 15, 17 is greater than 15, 25 also is greater. So it's also okay. And the left right subtree, which has the root value 20, we can see that 17 is in the left part, which is less, so it's okay. 25 is the greater part, so it's also okay. Now we don't have to see it for the leaves because they don't have any more children. Okay, now what happens if I change 12 with 16? I'll not change, I'll just write. We can see that for 10 as a root value, it's still possible because 8 is on the left side and it's less, and 16 is on the right side and it's greater. But if we take this whole root value 15, we see that 16 is on the left but it is greater than the root value. So this will then change the binary search tree and it will no longer be a balanced binary search tree. So we cannot change the value from 12 to 16. Now let's see how we can only take the average case. Okay, now how it is big O of log of n. In binary search tree, we start with n elements in search space, but we have to target the middle element, which is in the first, it's 15. So we target the middle element, and the number of elements then goes decreasing to n by 2, and slowly it goes to n by 4, and till you get your finding element, or till the elements become 1, or the last element is left. Okay, so suppose I have to find 17. So I go to 15, I check whether it's greater or lesser. 17 is greater than 15, so I discard the left part of this binary tree, and I only search the right part because I know it should be on the right part as it is sorted. Now when I go to right part, I go first check with 20. Now checking it with 20, I get that 17 is less than 20, so it should be on the left part, left child. It should be with the left child of 20. So I go to 17 and I check that 17 is I got my value. Okay, so in 3 steps I got my value, but if it would have been an array, I would have to search from start till end, and I would have to find the value of 17 somewhere in the middle. Okay, now we can see that a number of steps always gets equal to log of n. So we can say that the search complexity, cost of search, is always big O of log of n. Okay. Now what if we want to insert a value? Okay. So while inserting the value, suppose I want to insert 19. Okay. So if I have to insert 19, I will check from 15. 19 is greater, so it will go to the right child. Then we check from 19. It is 19 is less, so it will go to the left child. Then 17 is less again, so 19 will just come and stick here. Okay, because it should go on the right because it is greater than 17. Okay, Now, sometimes in binary search tree, which is basically a traversal in which we go either to the left or the right, and we just keep on removing and discarding a subtree at each step. Now, I told you the word balanced binary search tree. When is the binary search tree balanced? We call a tree balanced if for all nodes, the difference between the height of the left and the right subtree is not greater than 1. So in here case, we can see that left and right nodes have equals, so the difference is 0. But we can go to the maximum of 1 difference. Okay. Now let's see an example of unbalanced. It will be a binary search tree, but unbalanced. We'll present the same tree mentioned above in a form of unbalanced search tree. So I'll just make this 25, 20, 17, 15, 12, 10, and 5. Okay, so this is again a binary search tree because it's all the left nodes are lesser and lesser and lesser and goes down, but it's not balanced because there is no right child and it cannot be balanced. There are all the elements are in the left child only. Okay, so this is a binary search tree, but it's not balanced. So, and if we search an element as this, then we get the cost as big O of n, which is the worst case. But we don't want the worst case. So it should always be balanced in a binary search tree if you want to be the average case and you want the time complexity to be big O of log of n. Okay. Now we'll take an example again. Okay. With this way you'll get easy. You can understand easily. You had a binary search tree, right? Now we'll take a balanced one, but it will be different from what I told you earlier. This one is perfectly fine. This is the perfect binary search tree you can make. Now I'll take an again balanced search tree, but this will not be the perfect one. So I take a 12, 8, 15, 10, 17, 20, 25. Now the difference on the level of left right subtree and left subtree is 1, you can see. So it is balanced, but by any means it's not the perfect binary search tree we are looking for. BST gets unbalanced when you search or remove an item. So now when we see this, we just insert in 19, right? So it gets a little unbalanced. It's still balanced because there's a difference is 1, but it gets a little unbalanced because earlier it was perfect. While removing also, if I remove 17 here, then the tree will get unbalanced because there is only 125 here and then one of the elements is missing. It will get a little unbalanced. So we can see that binary search tree is very efficient. Whether we search, insert or remove, we get always big O of log of n. So it is very efficient for searching elements. Okay? So this was the basics of binary search tree. That's all you need to know, and how do we search and how do we do everything. Okay, so we always target the middle element and then keep on searching the left and right based on whether the value we want to find is lesser or greater. That's all for binary search tree. Thank you.
Now let's talk about the additional learning which I've been doing in data structure and algorithm. The course title is Algorithmic Toolbox. It is a course from Coursera, and it is being taught by the professors of University of California, San Diego. The program basically includes everything basics about algorithms. And it is a 6-week course, and I've already completed a week 1 in which I have learned about how to make a program, how to check the validity of a program using random variables, and the random variables can be inputted by the system itself. We don't have to input it by ourselves. So it checks all the possible cases for a algorithm. Now the second week, which I just started, I've been learning how to make an algorithm more efficient, how to get a more efficient algorithm rather than a naive one. So consider an example. You have to print the 100th element of Fibonacci series. So there might be an algorithm which might take a recursive algorithm which might take extremely long time to give us the result. But at the same time, there might be another algorithm which just takes a few steps and gives us the result and doesn't even take a long amount of time. Okay, so I've been learning this, and in the coming weeks, as I've read the course contents, I will be learning uh, about different types of algorithms like divide and conquer, greedy algorithms, and I would be doing a lot of programs related to those types of algorithms, and one of the main programs, and I would be graded on a basis of the questions in programs they give us to write. So it's a very good course. I have been already getting a good sense of algorithms as a whole. Now let's move on to J component. The project title of my J component is College Record System. So in this project, me along with my two other teammates are basically making a record system for colleges to store students' data, like in using file handling. So, like you want to input students' data, their registration number, their name, their roll number, everything, and then you can create a copy of that same file, whole directory, and then you can even delete something. You can search the students' details using their just name, roll number, anything. So it's a very efficient way. And my part in this program and in this J component is that I will make the main function in which I will incorporate all the functions and classes that my teammates will make, and I will make it more efficient. And I will take input from the user, and using switch case, I will call each function one by one, and and then I will make the program run. At the end, I have to take all the file handling and the functions, and I have to debug it if there if there is a difference of variables of same, but it should be of same type. So I will make those changes, and I will debug the whole program and make it to be able to run. So that's all about my J component and additional learning. Thank you.